Hello! This section is designed to introduce basic concept of electronics to a person who never dealt with such non-concepts before. The section is split onto 3 subsections. We will start with introducing the basic components. We'll describe its functions and behavior, and then we will continue with more applied concepts such as amplifiers and filters. But first, let's talk about the electronics from a perspective of a layperson. On the screen you can see a picture of 2 people. Can you spot an electronics engineer? Right, the person on your right you all recognize. It's famous Steve Jobs, the founder and spiritual leader of Apple Incorporated. The person on your left, however, is less known. It is Steve Wozniak, the principal electrical engineer of Apple and the actual creator of all early Apple products. But you can see what I mean. It takes a specific kind of person to be an electronics engineer. You have to read and understand very complicated, impenetrable diagrams. You got to spend almost all of your time in a workshop with no natural light, surrounded by the massive amount of quite complicated equipment. And you got to speak a specific language which is only spoken by geeks like you. Which brings us to the next question. Is electronics even relevant? And the answer is absolutely. And not only for biomedical engineering. If you look at any modern product, be it consumer or specialized, it will always, and I mean always, contain electronics. Starting from cars, which is an example of very conservative industry, and finishing things like MRI scanner, where electronics contain more than 50% of its sheer weight. Well, it's all fine, but is it not depressing that you gotta be a geek to understand any contemporary product development? Well, the thing is that you don't have to be an electronics engineer nowadays to be able to design and evaluate engineering systems. It can be much more fun than the other Steve. Similar to almost any engineering discipline, there are layers of abstraction you can operate with and still be able to do things. The common example is a cell phone. The fact of the matter is that in modern world nobody knows how to build one from scratch. And further, you do not even have to know anything about the electronics to be able to write programs which run on the phone and use its electronic features, thanks to the modern-day high-level programming environments. Things start with a silicon chip, a physical piece of embedded electronics packed into a very limited space, which can be represented as a circuit diagram, which in turn can be described as a mathematical model. You do not have to know the exact chip structure to understand what it's doing and how to use it in your own product. Although you still need to learn the limitations of the abstraction, as you don't want surprises to be revealed after the product is already in production. But as soon as you operate within those limits, you will be safe. No, really, the entire thing can be replaced with one diagram and a model. We can call these models as transfer functions, and we will talk about them in detail during the second lecture. But the simple idea is that any system can be represented as a function in Laplace domain which has inputs and outputs. By knowing this function, you can predict the system's behavior, analyze its performance, and because someone else had already done the work of proving it, you can be sure that the actual system behaves exactly as intended when integrated into the product. Right. When we talk about electronics, there are 2 main areas it can be divided into, and it is a direct consequence of the types of information that the electronics bit is dealing with. They are analog and digital. Analog electronics deals with continuous signals, meaning that at any time point there are a value of a function we consider, and it can be any value. Digital electronics operate with discrete signals, meaning there is limited range of discrete values, and they are defined over discrete time intervals, also called sampling periods. The basic comparison between the 2 is real world versus things computer-like. Digital electronics, a thing that computer-like, operates with pulses, the most common of which is on-off pulse. That means that you only have 2 values and the signal can be on or off, and it can be obviously code binary information. In real life, you would deal with certain voltages like 0 for off and 1 or 5 for on. With the correct circuitry, this kind of signal is very robust to external noise. You can see on the picture that even if you distort the original signal a lot, With the selection of appropriate threshold, you can achieve near perfect recognition of where is on and where is off. The most common thing to do a job is a Schmitt trigger, which does exactly that, exists on every Arduino digital pin and ensures the robust detection of pulses. On and off pulses can be used to transmit something more advanced than a digital information. You can vary the time on on versus off pulse over the specific amount of time and get so-called duty cycle, which is equal to a pulse width, the time the signal is on, over the total amount of measured time times 100%. If you have several consecutive pulses, you can transmit some information by encoding it in a pulse width. The beauty is, if the system you transmit this information to cannot react fast enough to each pulse, like a motor or LED, then your actual power voltage that the system extracts from these pulses will be equal to the duty cycle time times the amplitude of the pulse. The motor, due to inertia, will not react fast, so its speed will be modulated by duty cycle of the pulses that you send. Each consecutive pulse will push the motor, and amount of additional speed is received each time will be proportional to the amplitude of the pulse times the pulse duration. Thus, if you can do it fast enough, you can control that precisely. As mentioned before, duty cycle is quite powerful tool to transmit analog information over digital world. And many microcontrollers, including Arduino, will have this functionality implemented by default. The standard name for technique and circuitry is pulse width modulation. One of the brilliant features of digital electronics is simplicity of implementation of formal binary logic. There are standard digital components for logical operations, such as AND, OR, XOR, and NOT. The simplest is NOT, which flips the voltage and therefore makes zeros where there were ones and ones there were zeros. You can read about the rest of them and how they operate online, but the idea is that you can build every sophisticated machine using only those. But lots of them together, add some memory, and very broadly you made yourself a microcontroller. Okay, the digital electronics is brilliant, but how do we convert our real-world signals into the digital world? The specific tool to perform this function is called, surprise, surprise, analog to digital converter, or ADC. It takes the input signal, most commonly voltage, and produces the binary output, sequences of pulses. The most common of them would have one input and several outputs. Each output would binary code its specific register, and inside there will be some sort of threshold detector. It can also be a Schmitt trigger. The input signal goes to each detector, which turns 1 if the threshold is met. If the thresholds are algorithmically scaled with base 2, each gives you a binary digit. If your signal is small, then none of the detectors worked and the output is 0, 0, 0. If you start increasing it until the lowest threshold is met, then you get 0, 0, 1, and so on. Obviously, there is circuitry which controls compensation voltage for every threshold activation, but it's quite easy and operates as a subtraction feedback for each register. There are different types of ADCs which operate at different accuracy level, which is also called resolution. The sophisticated go up to 24 registers or bits, which mean they can code a lot of numbers precisely 2 to the power 24. They also operate at different frequencies, sampling rates, and normally sampling rate trades off resolution and vice versa. Coming back to digital versus analog electronics, there is a simple diagram of pure digital circuitry, also known as digital clock. It normally consists of blocks connected to each other with wires transmitting binary signals, on-off signals. Here, for example, is the pulse generator connected to a clock divider that slows down the clock to once per second. Then counter, which counts up to 8 pulses, and then binary LED control for the LED display, which in turn drives the actual LED display. Digital electronics is very easy to design, everything is standard, but it's generally expensive and requires more energy to do the same job. Analog electronic circuits are more complicated and components are inherently analog. This diagram shows filter, buffer, amplifier, and then current converter and speaker. Altogether is known as consumer amplifier. The analog stuff is more complicated and noisy, so the rule of thumb is to use digital unless you cannot. Now, to the question of schematics and basic components, you should know about resistors and capacitors, got to be the school stuff. So we will start with bypass capacitors, a specific set of capacitors commonly connected to the digital electronic circuits. They exist to reduce the noise from the power supply to the electronic components, having much lower impedance for higher frequencies than for lower, and act as a no connection for lower frequencies and straight wires for high frequencies, shorting all high frequency noise to the ground. If we read the digital circuit, we can simply ignore them for the purpose of understanding how the diagram works. The next essential component on the list is a diode. It is a semiconductor device, which means that it can only transmit current in one direction. This direction is called forward, from so-called anode, positive voltage, to cathode, negative voltage. If we apply inverse voltage, positive to cathode and negative to anode, current will not flow, and diode is reverse biased. If you know Futurama and got the joke, you have understood this slide. So when you see a diode in the circuit, you can simplify by assuming no resistor in one direction, straight wire, and infinite resistor in another direction, which is a gap. The most common and simple use for diode is current protection. It is, if you remember 70s and 80s toys and importance of misconnecting the polarity of the battery, you understand the simplicity and brilliance of protecting the expensive stuff from complete burnout by inserting a simple diode either forward way on positive pin or reverse in parallel. Please take time to analyze what is happening on the screen and what is the difference between these pictures. In reality, however, diodes are not ideal. They need certain small voltage, forward voltage, to start working, and they do not hold infinite reverse voltage. The maximum is called breakdown voltage. Also, they can only transmit limited amount of current before they start to heat a lot. Some diodes exploit these properties, and then they are specifically marked on the diagrams with the funny symbols. For you, however, it's enough to say, it's a diode, I know what it's doing, move on, or Google the specifics if you need to. The particular interesting type of the diode world are light-emitting diodes, or LEDs. As name suggests, they emit light when forward biased, and as they are love and joy of every engineer and keystone of modern consumer electronics. The luminosity of LED is proportional to the current flow. Maximal current at which diode starts to be a flaming sword is limited at much lower values than traditional diode. So it is a good idea to add some resistor in series, which is called limiting resistor, to avoid overheating issues and power fluctuation troubles. However, in more precise application, where luminosity is a factor to control, it might be necessary to control the current directly supplied to LED. The other type of commonly used diodes is a photodiode. Based on the photoelectric effect, this guy acts as an inverse of LED and generates the current which is proportional to the amount of light reaching the active photoelectric element. Depending on the composition and structure, they can generate lots of current, but then they react slowly, or can produce low current but act fast, which is a great solution for sensors. They are commonly used as a receiver for remote controls of the consumer TVs. The current generated by the diode is proportional to the incident light, so the circuit can be greatly abstracted and simplified. There are many types of them, some of which are sensitive to specific light wavelengths, and some are directionally sensitive. Again, think of them as inverse of LEDs. Moving on, we're now at the doorstep of the most critical component for any electronics, a transistor. A semiconductor device has 3 pins and acts as either insulator or conductor. Between two of them, they're normally called collector and emitter, C and E on the diagram, depending on control signal applied to the third, which is called the base, or B on the diagram. To put it simply, it can be described as a control valve for current passing through it, or a variable adjustable resistor. Depending on the operation mode or semiconductor physics, they can be PNP, where more base current means more output current, or NPN, where more base current means less output current. Their main applications are switching for digital electronics and amplification for analog. They're great for switching, where you control the flow of high current, normally high power to some heavy-duty appliance, using low current, normally battery-driven or supplied by a microcontroller. Real transistors will not have infinite switching speed and will have a maximum current you can supply to the base, and so used with the limiting resistor, and minimum resistance at fully on mode. if you see a base pin of the transistor on the diagram connected to a microcontroller digital pin, it is probably used as a switch. Amplification properties of the transistor can be leveraged if the base pin is connected to the low power input signal and emitter connected to the ground. These can produce high voltage gains and are commonly used in analog guitar amplifiers as is. So if you see a base of a transistor connected to an input signal of it on the diagram, it is probably used in amplification mode. There are many types of transistor and transistor-like components. Some of them are voltage controlled, and if you want to know more, Google and Wikipedia contain more than enough information about them. So the general rule, do not know something, Google it, works the best. Well, finally, now we know basic components, let's consider some circuits. Since we will look at both analog and digital electronics, let's review 555 timer. Inside it is actually quite complicated, but as always with digital, we can just consider the IC block only, which is displayed on your right. As we know already, bypass capacitors can be ignored, and the rest resembles a connection of R's and C's, which we will talk about later, but in principle is that a capacitor takes time to charge and discharge. And this time depends solely on the combination of capacitance and resistances around. We can use this to construct a circuit which will charge and discharge the capacitor upon reaching a certain voltage threshold. It can be easily implemented using digital logic, and this is exactly what 555 timer does. So the circuit is delivering pulses with a fixed period, which are solely dependent on 3 analog components and can be easily controlled. Hello! As the name suggests, we're going to be talking about the signal amplification in this lecture. First of all, why do we need to amplify the signals? Well, first reason is simple, because any signal that you can physically collect from a human body is small, especially electrical signals. On the map of the signal scales versus the frequency content, the smallest will probably be EOG, or electrooculography, which measures eye movement using a set of 3 electrodes located on the head. These have range of 10 to the minus 5 volts and frequencies of around 1 Hz. You cannot move your eyes faster than 10 cycles a second, can you? Then we have EEG, electroencephalography, which measures electrical potentials from the surface of the head generated by the neuronal electrical activity within the brain. Typically, it is tens or hundreds of microvolts and resembles average neuronal electrical activity of the cortical regions. ECG, or electrocardiography, measures electrical potentials from the surface of your torso generated by the muscles of your heart when they are contracting. These are typically around a millivolt and are a vital component in clinical and hospital care. And yes, now you can even have a business card measuring ECG using the potentials between your fingers. EMG, or electromyography, measures potentials generated by electrical activity of skeletal muscles. They are similar to ECG, but a bit higher since you can measure them from the surface directly above the muscle of interest. There are tens of millivolts and form a basis of many active bionic prosthetics. Right, so we have a signal that is at most millivolt, which we need to send to the microcontroller and make it digital. Digital is better than dealing with analog electronics. Remember, at least you can store digital in computer or something. Normally we would have limited bit resolution and supply voltage of a scale of 5 volts, meaning that our entire signal does not cover even a single bit. We will not see anything basically. So yes, we need to fit the signal to ADC window. But that is not all. We also can improve the condition of the signal. As we all have learned by now, pure components do not exist. Wire is a resistor. It has also inductance and capacitance coupling. These produce all sorts of effects, especially if located very close to each other on a PCB. Look at all the mess we need to deal with when consider everything properly. That is practically impossible. We cannot ignore that as it is, especially considering the fact that our signals are weak, and amplification is a great way to condition our signals so they learn to ignore the parasitics. So we start with the cornerstone of any amplification circuit, the operational amplifier. It has 3 digital pins, V+, V-, and V out, and 2 pins for power supply, VS+ and VS-. Ideal op-amp does very simple task. It amplifies the difference between V- and V+ with a constant amplification coefficient. Obviously, ideal op-amp would do this thing instantly, produce infinite voltage and have zero effect on input signals. Right, this is a schematics for a common one. It probably has some limitations, which are many. For us, however, each individual parameter does not matter, and we can summarize op-amp properties using only 6. Open loop gain, input impedance, output impedance, offset, CMRR, and bandwidth. Open loop gain, the stuff that you need to multiply your input to get your output, ideally we want it to be infinite. We will see why it is important later, but typical op-amps have it from 2 to 200 Ks. Input impedance, the stuff which resists the current flow between minus and plus. We do not want this, otherwise the voltage divider forms serial to source. Essentially, we're measuring the voltage across input impedance of the op-amp, and if it is small, as shown on the diagram, we lose large portion of the total voltage supplied. Output impedance, this stuff we want to be zero, otherwise our current is limited by external components. Besides, there is another voltage divider forms and we are losing another portion of our signal. Offset is the stuff which shifts our signal. We would expect zero if V1 equals to V2 or V- equals to V+. In reality, however, very small voltage always persists, and if we want it pure, some specialized circuitry is needed for compensation. CMRR, or common mode rejection ratio, is another vital parameter. This tells us what happens if we have two large but equal common signals coming to V+ and V-. Obviously, we will expect zero, which makes CMRR to be infinite. In reality, it is 80 to 100 decibels, which means some fraction of common mode signals come through the output, especially this is important if it is 50 Hz mains. The real op-amp can also saturate. This normally happens when the output voltage needs to exceed the supply voltage. So the op-amp cannot possibly produce this and outputs all it can do. This is not only distorts the signal, but also causes op-amp to recover, which can take more time than expected. The last but not the least, we would like our amplifier to amplify every frequency equally and do not disturb our signal. In reality, starting at some point, the gain of the op-amp will decrease with frequency. This often causes signal distortions and delays. We normally can characterize the open loop gain across frequency as two lines in log scale. First line show roughly constant gain up to a certain point, called breakpoint or -3 dB point, after which the gain typically decreases with a rate of -20 decibels per decade. When you read the specification of a particular op-amp, it will have AOL in its datasheet and also gain bandwidth product, or GBP. This describes the decrease in gain as bandwidth increases. You can build up the frequency characteristics of the op-amp knowing both. GBP also shows at which frequency the op-amp becomes unity gain or stops amplifying at all. GBP is very common characteristics of the op-amp and plays key role in constructing actual op-amp based amplifying circuits, and defines maximum gain of a closed-loop amplifiers, as we will see next. Right, as you probably guessed, nobody uses op-amp as it is in an amplification circuit. The most common circuits involve feedback. On your screen there is a typical schematics of such circuit. Let's analyze this quickly using the control theory. For those of you who don't know this stuff, don't worry, next section is all about it. For now, just relax and believe me, you can always come back and check my working out later. So the voltage out to voltage in ratio according to this is AOL over 1 plus beta AOL. And in ideal case scenario, AOL is infinite, so it's just 1 over beta, where beta is a constant dependent on the peripheral resistors. Well, this is cool, as we have an amplifier which gain depends only on the external resistors. And to change this, we do not have to change the actual ICs. Yay! Imagine the level of flexibility. This is why op-amp is so commonly used. The op-amp circuits with negative feedback, meaning the output is connected somehow to a negative input of the op-amp, is very easy to analyze. You do not have to know control theory, and you only need two rules. Rule number 1. The op-amp will do whatever it takes to make V+ to be equal to V-. And rule number 2. Inputs draw no current. If you know these two rules and Kirchhoff's laws, sum of currents in the node is 0, sum of voltages across closed path is 0, you can literally crack any op-amp based circuit like that. Let's practice on this one. So V1 equals V2, and since V1 is connected to the ground, it is 0. Now, according to rule 2, current through Rin should be equal to a current through Rf. Expressing voltage drops across both, we can relate V in and V out as the following. Ta-da! We have an amplifier with an amplification factor of minus Rf over Rin. Note that the voltage is inverted, so we call this an inverting amplifier. Let's come back to the non-inverting amplifier. Writing down two rules, we can instantly get the V out to V in relation and compute the amplification gain. Right. What if Rf is 0 or R2 is infinite? The gain becomes 1. Or we can draw it like this, hence commencing both assumptions. You would probably ask, what? Unity gain? Who needs unity gain? What are you achieving with this? Well, remember the conditioning of the signals that we were talking about. This plays a significant role in such conditioning. We can basically break the signal to before and after and consider them separate. So every time we change something on the left-hand side, it doesn't affect the right, and vice versa. Also, we can draw much more current into the system and hence pumping the energy into the circuit, preserving our signal at the same time. Finally, using negative feedback loops and op-amp, we can also see how the frequency response reacts to the closed-loop gain given fixed GBP. Basically, for higher gains, our bandwidth is small, open-loop gain being the maximum we can achieve. Reducing the gain literally gains us the advantage in bandwidth. And in every case, the product of 2 equals to GBP. Actual characteristics of closed-loop performance are typically listed on the datasheet of the particular op-amp. The rest is literally yours to decide. See you in the next lecture. Hello! In this lecture, we're going to talk about filters, and specifically electronic filters. First again, why do we need them? Well, it all comes down to a point we made in the second lecture. Our signals are small. And whilst they're traveling through various cables, they get contaminated with all sorts of noises. Add to this parasitics, 50 Hz mains frequency noise, and all sorts of unwanted signals which are present during the signal acquisition, and we end up with unwanted mess on top of our small but valuable signal. So we use electronic filter in order to essentially filter out signal out of the unwanted components. Most commonly in engineering, we're talking about filters in terms of the frequency content. So instead of the common time domain, signal changes in time, we use frequency domain. You can represent a single frequency sinusoid as a point in frequency domain with the x-axis denoting the frequency of the sinusoid and y-axis representing the amplitude of the signal at that frequency. If you feed the sinusoidal signals with unitary amplitude to the system, you will get so-called baud plots or baud diagrams, which show amplitude and phase response of the system at any given frequency. If you look at this example of the first-order low-pass filter, you can see that at small frequencies a sine wave will pass through the system almost undistorted and will have the same amplitude and phase as the original signal. If you have a very high frequency, you can see that the sine wave at that frequency will be reduced by approximately 70 dBs and will be antiphase, which means that the voltage is inverted. This brings us straight to the classes of ideal filters that are there. The first one, example of which we have just seen, preserves or passes all the frequencies up to a certain one, which is called a cutoff frequency. It doesn't let any other frequency which is higher to this to go through. This is called low pass. Depending on the location of frequency content of stuff that we want versus stuff that we don't want, there can be also high pass, band pass, and band stop or notch. The ideal filters are called brick wall filters, obviously, and do not exist. As we know, parasitics and physics limits us, so we end up with something on the diagram where we have certain characteristics of a filter which tells us how good or bad it is. The common are stop band attenuation, cutoff frequency or -3 dB point, and passband ripple and stop band frequency. Obviously, they are all related to each other, and in reality we need to pick the parameters that are more important than others in order to find the right compromise. Besides the obvious, another crucial application of filtering is the reduction of artifact caused by sampling, or aliasing. For a given sampling rate, there is a maximum frequency which can be sampled at that rate. It is equal to half of that frequency theoretically and is called the Nyquist frequency. Below this frequency everything is okay and we can sample. Above, and horrible artifacts arise. It is also known as folding. The mechanism of this is illustrated in the diagram, where in the bottom case you start sampling things slower than the sinusoid makes a complete cycle. This can cause all sorts of artificial signals contaminating your original, just because they have higher frequencies than Nyquist. To avoid aliasing, you can simply implement a low-pass filter just before sampling, with cutoff at half of the sampling rate, thus removing troublemakers before they can cause any damage. The industry standard, however, implements harsher troublemaker removal techniques and sets cutoff somewhere between 1/3 and 1/4 of sampling frequency, depending on the application. At this point, we will take a slight U-turn and talk about transfer functions. Do not worry, we will come back to practical stuff shortly. Just bear with me for a couple of minutes. The need for this particular abstraction comes from our desire to describe systems not only in frequency domain, but also changing in time. Things start when we describe the system behavior as an ordinary differential equation with respect to time. Think of a second Newton's law, where you have acceleration, second derivative, and velocity, first derivative of position x. The input in this case resembles right-hand side of the equation. In Newton's law, it's the force. And output is the stuff we need to find. In Newton's equation, it's the position. So for a known input, we can compute the output if we know how to solve those. However, this is bulky and does not let system identification and analysis. Instead, we will introduce something new. We will only consider linear time invariant systems, which most of the electronic components are, and the ones which are not can be linearized. If you have this system and have its ODE, then you can perform a so-called Laplace transform. This is weird transform which is equal to the integral from 0 to infinity of a function self multiplied by e to the power of minus st, and takes us to a different space called Laplace domain. It is the extension of the Fourier transform, and similar to a Fourier transform, gives us a powerful tool to analyze dynamic systems. The principal variable s is an extension of Fourier's frequencies w of the complex plane. Together with some exponents, it is easy to see when exponential term is 0, i.e. we're on the imaginary axis of S-plane, and the transform simply becomes a Fourier series. The beauty of Laplace transform is that it transforms all derivative to multiplications by s. Same is true for nth derivatives, it becomes multiplication by s to the power of n. Also, it transforms all integrals to a division by s. This is very handy. Now, all your complex ODEs becomes algebraic equations. And on top of this, there are standard transforms for many functions, which you can use to get back to time domain after you have solved algebraic equation. Yay! For us, however, the Laplace transform itself has much bigger value, which we will see later. But enough theory, let's practice some Laplace. Consider a spring mounted to the wall. For me, it is always easier and more intuitive to analyze the mechanical systems. Time domain equation is well known, it's a Hooke's law. Force is proportional to a deflection. Position, assuming 0, is where the spring is not deflected. K is the stiffness coefficient of proportionality. Let's take Laplace transform, remembering that force is the input and x is the output. The transform is actually quite easy in this case, as there is no derivatives. Then our task is to find the ratio between the output and input. And voila, we have found a transfer function of the system, which definition is exactly this. It is the ratio between output and the input in Laplace domain. Now, to find an output of the system to any input, we just need to multiply the transfer function by the input and take inverse transform. So transfer function for the spring is just 1 over k. Let's see what happens with electronic components. Resistor, following the Ohm's law, and assuming the input is voltage and output is the current, has the transfer function 1 over the resistance R. Similar, the capacitor, with a mild complication in replacing the time derivatives for multiplication by s, has a transfer function Cs. The inductor, 1 over Ls. Let's see some combination of components, and this example is a bit more complicated since here we would like to find the ratio between input and output voltage. Right, we will start with expressing what we know, and note where we measure all the voltages. Applying Kirchhoff's laws and Ohm's law, we substitute and get a time domain ODE, which can be easily converted to a Laplace domain. And finally, the transfer function can be expressed using some constant substitutions as gamma over 1 plus tau s, where gamma, which is called the gain, is 1, and tau, which is commonly called the time constant, is equal to RC. Okay, Sherlock, now what? Well, it gets really cool when you consider the fact that you can instantly get a frequency domain response, a Bode plot, by ignoring real components of S. Substitute j omega into the transfer function, and here you go. You haven't only found the entire frequency response, you have also instantly found the -3 dB point or cutoff frequency. I will leave it for homework to digest, which is in this case is simply 1 over RC, or in terms of actual Hertz frequencies, 1 over 2 pi RC. Yes, as you have probably noted, this is a low-pass filter after all. Remember the statements about capacitors? Well, now we know much more about how exactly the current does or doesn't flow through the capacitor and at which frequencies. Moving further, using the resistor and capacitor, it is easy to create a high-pass filter as well. Logic tells us low frequencies current will not flow through a capacitor, high frequency will. Transfer function tells us the exact value of the cutoff frequency, which is 1 over RC, and lets us plot Bode diagram of this filter. But the beauty of the Laplace doesn't end there. If you do not drop the real part of S, but instead give the system some extreme input like a step function, for example, the transfer function can tell you what exactly your system would do. In case of first-order filter, for example, we can observe the time delay. And we can say a lot about this delay by looking at the transfer function itself. For first-order transfer function, there is a reason that tau is called a time constant. We will consider later what happens exactly when you increase the order of the system. But in general rule of thumb for filters is that if you improve the frequency response, but you also increase the initial delay and increase the time for system to settle down from a kick. Well, let's see. If you have an RC filter, quickly enough you realize that it's too simple, lets too many frequencies in, and you might want to double it. Logic tells you that it will work twice as good, right? In fact, you might think infinite number of them would produce you an ideal filter, right? This is also called cascading. First thing to consider is that the gain is not actually 1, and there is a reason for it to decay towards the -3D point. So every time you do that, amplitude decays ever so slightly, or not slightly depending on the situation. Second thing is, let's see what we want to get. Second order RC filter, V in, V out, one transfer function, another transfer function. It's not just a multiplication? Well, intuitively you understand that voltage at point A actually depends on all 4 components. Let's formally derive this. From Kirchhoff's laws, at point B we get the following. Same for point A. Substitute 1 into 2, and after rearranging into transfer function, you get the following monster, which after tidying up looks nothing as we have hoped for. In fact, it is actually a bit tricky to analyze. Can we make a better system? Well, yes, that's why we introduced the buffer amplifier earlier. Let's stick it in between the first and second filter stages. Now everything is independent, and we can simply multiply 2 transfer functions together. This is the answer we want. And now we can control each filter independently as well. However, still some poor performance due to the output impedance, the one that loses our some voltage, being determined by the second RC filter and thus poor, not the end of the world, but not perfect. Oh well, the glory of adding another buffer at the end and making everything right again. Do not get me wrong, this is not a perfect system and had drawbacks, but way better than passive cascading. To solve the issues of this system, however, we can introduce more sophisticated filters. Cell and key, for example, has only one op-amp and also has 0 output impedance. It can also be implemented in combination with the amplification in the same circuit. Gain here is defined by the ratio of 2 additional resistors. However, it alters the frequency response. There are many other topologies of the active filtering, all of which would have slightly different characteristics. And I am sure you can find your ideal filter now when you know the basics, and after we have talked a bit more about the transfer functions in the control theory section. Okay, so we have talked about filtering in the frequency domain, but what if it's not enough? What if our noise exists in the same bandwidth as our signal? Well, the solution to this is a coherent averaging. If your signal is repeating, you can log into the event you're interested in and add together several of those. The idea being that your signal is locked into the particular event like a heartbeat, and your noise isn't, so it will be random with respect to the event, thus eliminating is 1 over root square of n, where n is the number of repeats. You can read more about this technique if and when you came across the specific problem you need to solve. Finally, and I must stress this intentionally, please always bear in mind that 1. Filters are not magic and nothing can recover missing data. And 2. Filters can only reduce the noise by a limited amount. So if you have enormous amplification and then filter, there is a possibility that noise will still be an issue. So overall, remember the following rule: filters are not a substitute for a good data. See you in the next lecture. Hello. In this section, we're going to talk about the control theory, which is a crucial part of any engineering, especially electronics and robotics, which are the part of biomedical engineering. We will start the lecture from reminding ourselves about the transfer functions, which are touched in the first section briefly. Remember the transfer function of an RC filter. Also remember the second-order RC filter, where we cascaded 2 of them through a buffer. Here, we're going to learn how to analyze those transfer functions, and how to design effective controllers in order to improve their performance. First, let's remind ourselves how the first-order transfer function looks like. If we apply the inverse Laplace transform, which we can simply find in the standard table, we can see that the solution to the ODE, or system response in time, is always structurally the same for any first-order system, and equals to some exponent multiplied by a coefficient. If the tau is positive, which is always the case for an RC filter, it is basically decaying exponent, with the gain defining the starting point and time constant defining the rate of decay. As an example of a second-order transfer function, let's consider a mechanical system of a mass supported by a spring and a damper, essentially a shock absorber in a car. This system gives very good intuitive understanding of any second-order system, as all of the constants have real physical meaning. First, we as usual write the equation of motion, which includes inertial force, Hooke's law for a spring, and viscous damping. The one proportional to the velocity, or first derivative of deflection. Here, external force is the input, and the mass deflection is the output. The Laplace transform replaces all derivatives to the S multiplication, and some rearranging brings us to a transfer function for this system. Now let's redefine some constants, and now we have this written in a standard form: gain, natural frequency, and damping ratio. You can instantly see the amount of useful intuitive information you can get about the system just by knowing those constants. This function is known as a damped oscillator, in that it produces harmonic sinusoidal oscillations which decay over time. This type of system appears everywhere in physics as well as in engineering, even to the extent that some higher order systems are simplified to become second order, just because it's so well understood. Another useful example for us is a servo motor. As you can imagine, those are used everywhere in robotics. And for us it is important as it is a key component for active prosthetics. Here we have the angle of rotation as the output, a motor torque as an input, which we can control by voltage or current directly. And it has viscous friction in the bearings and inertia. The ODE can be delivered through momentum balance equation. And by taking Laplace, we can see that the transfer function has similar structure. However, there is no spring element. Several systems can be obviously combined together, and it is easy to see that a combined transfer function of a chain of several transfer functions can be found by a simple multiplication. The crucial component of the control theory is the feedback. As the name suggests, to organize the feedback, you need to measure the output, transform it somehow, and feed it back to the input. Remember the op-amp and the multitude of nice properties that we have achieved by doing so. In control theory, to describe this process, we add a summation element, where we put plus or minus near the signal path to indicate whether we add or subtract. In most cases, we tend to use negative feedback loops, which means we subtract the modifier output signal from the input. The mathematics of computing the feedback or closed-loop transfer function is also straightforward. By careful tracing of all the inputs and outputs, we can do basic algebra and arrive to the equation. Similar, single transfer function can represent any complicated system, which involves electromechanical components, measurement of several parameters, and decision-making integrated into continuous process control. For example, part of Tesla Autopilot, which measures GPS speed and acceleration in order to maintain constant velocity, can be gradually unwrapped into a second-order transfer function. The rule here is to start working from the innermost loop progressing outwards. Handy. Remembering the transfer function of a servomotor, we can see how a simplest feedback of just subtracting unmodified output from the input changes radically its transfer function. Now the system can oscillate as if it had an artificial spring, and we can control the frequency and damping ratio by adjusting the parameters, for example gain on the motor. The last bit to consider about the second-order transfer functions is the generalized solution. If we look at the table of inverse Laplace transforms, we can construct the solution in time and see that it has a constant multiplied by exponent, which in turn is multiplied by a sinusoid. This lets us generalize the entire class of second-order system, be it car shock absorber, second-order RC filter, or servomotor. The dynamic response contains an oscillatory behavior bound by exponential amplitude. If damping ratio is less than 1, the solution is decaying sinusoid, where frequency and the rate of decay is fully defined by the constants of the standard representation of the second-order transfer function. You can see now the system step response, the usual measure of system dynamic performance, which we can easily compute knowing the transfer function and supplying step function to the input. The step response in Laplace domain is equal to A over S, where A is the step size. After multiplying, you can find the appropriate equations in the Laplace table, or use digital Laplace transform to evaluate the output. The damping ratio here basically controls how fast the system is reaching the target, versus how many oscillations you will get after the kickoff. More generally, the roots of the denominator actually control this, with standard classification of the system being under or overdamped, exponentially bound oscillations, critically damped decaying exponent, or undamped constant oscillation, depending on damping ratios. Hello! In this lecture, we will continue to analyze transfer functions and information we can get from them. Let's start by remembering the second-order transfer function behavior and the fact that it was controlled by the roots of denominator. We will formalize this for any arbitrary transfer function, denoting that any polynomial of nth order can be factorized by its roots. Since s is a complex variable, we always can find the complex roots. Now, the polynomial numerator of the transfer function will produce so-called zeros, the points where transfer function is equal to 0. The denominator will give us so-called poles. Both are important, and knowing all zeros, poles, and constant gain would completely define the transfer function and has the system behavior. Servo, for example, would have no zeros and 2 complex poles. A system is characterized by its poles and zeros as they allow the reconstruction of the input-output differential equation. It is possible to get a sense of the system dynamics from plotting the poles and zeros graphically on the S-plane. A pole is commonly represented by a cross and a zero by a circle. By plotting the locations of the poles and zeros on the complex S-plane, we can gain a considerable amount of information about the response of the system without having to take the inverse Laplace transform. Each pole corresponds to a component on the time domain response. So from the plot, it is possible to determine what component exists, their relative importance and possible simplifications, and how they change with gain. First, let's consider poles that have real components only. They will be located on real axis. They will transform to exponents in the time domain, and will be decaying if negative and increasing if positive. The relative position will control the speed of exponential increase or decay. If we have purely imaginary poles, they will transfer to pure sinusoids in time domain, according to Euler's formula. so they generate an oscillatory component with a constant amplitude. Poles closer to the origin have the low frequency, which increases the further poles are from the origin. If we have complex poles, it is easy to see that they generate oscillatory component bound by exponential amplitude. Poles located in the left-hand side decay to zero, whereas poles on the right-hand side increase to infinity, thus making the system unstable. The relative location and proximity to real or imaginary axis controls the speed of amplitude change and the frequency of oscillatory behavior. Now we can easily see what to do when deciding a controller. Basically, we can start with plotting original open-loop poles and decide what to do and how to move them around. For example, to stabilize the unstable system, we need to move all poles across imaginary axis to the left side. Now the rest is to decide what is there to add in the feedback to achieve that. Speaking of controlling different systems, it is important to know how accurately the control system tracks the demand, our desired input, once it has settled down. In other words, the steady-state behavior. For example, in case of step input response, does the system settle to a desired location or there is a gap? What is the system accuracy in tracing the changing demand? This can be evaluated by supplying the ramp input. It turns out both parameters can be evaluated using the finite value theorem, which takes advantage of some handy properties of the Laplace transform. The theorem says that the limit of the output when time reaches infinity will be equal to the limit of s times Laplace of output when s reaches zero. We are normally more interested in the final value of the error rather than the output, as the goal of the controller is to drive the error as close to zero. Further, for some inputs, such as a ramp or sinusoidal input, the final output isn't really meaningful. Normally, we consider the system we need to control in the forward loop, and stuff we are adding to the system or controller in the feedback loop. It is not what that is important, but drawing it like that allows us to compute the error quite easily as input minus output times transfer function of the feedback. From the other hand, output is equal to the error after summation element times transfer function of the system. Substituting and rearranging, we get the expression for the error through transfer functions and the input. Using the final value theorem, it is possible to find the steady-state error of the control system and thus judge the success of the controller without having to calculate the full dynamic response at all. Remembering how complicated it is using inverse tables combined with boundary conditions, we can appreciate the usefulness of this. For the arbitrary system, which has a feedback controller, we can deliver generalized expressions for the step steady-state error, which depends on so-called position error constant, and wrap steady-state error, which similarly depends on velocity error constant. Finally, to illustrate the point, we can compute the steady-state error of the simple feedback control servo and see that it is actually zero. I will leave it for the homework for you to evaluate the ramp response error, knowing that the ramp input is Laplace in the Laplace domain is a over s squared. Hello, in this lecture we will talk about the most commonly used controller out there. It is called PID controller, by the first letters of individual controller components, proportional, integral and derivative. Rumor goes that they account for nearly 90% of all use cases, which is a fine example of totally made-up statistics, but I would not be surprised if it's true. To see how it works and why it is used, let's start by considering each component independently. Note that we have transferred the controller from a feedback path to a forward path to illustrate the point of manipulating with the error. But this still is the feedback controller. So the proportional controller basically amplifies the position error. Let's see how it works. Formally, we can easily compute the new transfer function. If you evaluate the step response and track the performance, you can see that low values of Kp give stable but slow responses, and high steady-state velocity error. High values reduce steady-state velocity error, but response overshoots considerably. To understand why this overshoot occurs, let's look at the error term over time for a purely proportional controller for, say, a motor. With proportional control, the error and thus the control signal does not reach zero until the motor is at the desired position. However, due to the inertia of the system, the motor continues to move even without a control signal, resulting in overshot. Controlling the servo in this manner is like not applying the brakes until you reach the target position when driving. In reality, when driving, you apply the brakes beforehand, and also dependent upon the speed you are traveling. You brake earlier when you are traveling faster, or so I hope. We can replicate this by considering the derivative of the error. This is negative as the servo approaches the target, so offers a way of restraining the motor forward motion. Further, if we consider the integral or total error over time, this gradually increases over time and can be used to magnify the control signal for small errors and improve the steady-state error. In order to understand this formally, let's consider a derivative controller with unity proportional gain. Its open-loop transfer function is the following, and the closed-loop transfer function is on your screens. The closed-loop system is still second order, but now there is a zero in the numerator. The effect of this is subtle compared to the change in the poles. More importantly, the steady-state velocity error of this system can be computed, and we can see that unlike, for example, pure velocity feedback, the value is unchanged by derivative error. So overall, we can improve transient response without compromising steady-state error, which is great. The effect on the step response is following. The poles of the system becomes less oscillatory and decay quicker. This, combined with a reduced proportional gain, gives us an improved transient response. This is clear when looking at the step response and the relative contributions of the two error terms. At the start, the derivative term is significant and in the opposite direction of the proportional error term, but becomes negligible as the system settles down. The integral of the error is used for correcting steady-state errors, as it adds a pole at zero in the transfer function. We can see that by computing closed-loop transfer function and noting that now we have s cubed in denominator. Computing the steady-state velocity error, we can see that it is zero. Hey! If you look at the s-plane, you can see that the effect of an extra pole close to the origin, which would make our system very slow, is largely cancelled out by the nearby zero. This means that the system is broadly similar to a proportional controller with the exception of improved steady-state performance. Looking at the ramp response, it is clear now that the integral term has enabled proper tracking of a ramp input. This is particularly useful for overcoming steady-state errors arising from nonlinearities not included in the model, which prevent proper tracking in reality. Putting all three of these controllers together gives the complete PID. Here it is in all its glory. The closed-loop transfer function is rather big, but shows that it is possible to design a controller with improved transient response and decreased or zero steady-state error. In theory, just need to choose appropriate Kp, Ki, and Kd. There is no unique solution for the settings for these three gains, and so the values are dependent upon the specific system and the application. Selecting these parameters is known as tuning, and it was and still is in machine learning circles a very active area of research. Sometimes overshoot reduction is more important than settling time, like in heaters or ventilators. In other cases, reducing settling time may be the crucial and some overshot is an acceptable trade-off, like in camera focus, for example. Many methods of tuning these parameters exist and often form the first estimate before refinement based on testing of the real system. And finally, I repeat that these controllers are used everywhere and can often produce acceptable results even applied with little or no knowledge for the system being controlled. See you in the next lecture. Hello! In this lecture, we will learn about basics of coding for digital controller. Remember how digital electronics is much more flexible than analog. It is even more useful for so-called embedded systems, the systems which operate real-time and are used for 24/7 process, robot or medical device control. Broadly speaking, the boundary between embedded system and computer is thin nowadays, but we can divide by the following. The embedded system denotes reliable operations, task-specific and unlikely to be changed or tempered by the user. non-embedded, high-level, general-purpose, frequently updated or user-controlled. There are two common classes of embedded controllers: microcontrollers and field programmable gate arrays, or FPGAs. Microcontrollers are universal, versatile, they support high-level and generally can be used for anything provided correct embedded software, which is usually called firmware. FPGAs are pieces of hardware which can change physical states by a programmer. They are quick, reliable and parallel. We'll be considering only microcontrollers here, since what we need is flexibility, and FPGAs require some specific knowledge and skills for programming. Traditionally, the way microcontrollers are programmed includes three main components: the setup, main loop which runs infinitely and contains a set of instructions and statements executed consecutively, and interruptions. The latter are executed once upon specific hardware instructions. C language has been and still is the main language for programming those. It has official standard, but recently more and more languages, some of them are much more high level, are involved and being used in some industries as standard as well. Modern-day microcontrollers operate with much more user-friendly environments, offering high-level access for all its functions, so you do not have to know the specific chip layout in order to use the specific electronic features. The languages also, in most of the cases, already have a built-in libraries with simple functions offering more flexible and friendly way for coding. We will concentrate on Arduino here as an entry-level, hacker-friendly controller with lots of features and broad consumer-friendly and socially oriented support. You can start using it almost immediately, and all you need is to connect it to a computer via USB cable and start programming. Arduino programming environment, also called Integrated Development Environment or IDE, is free and easy to use. Once you loaded an example code or written your own, you need to select the type of board you have, which port it is connected to, compile, check button, download arrow button, and observe the operation. That is very easy comparing to some early days microcontrollers I have dealt with, which required 3 days to set up stuff just to be able to program it. The best way to learn it is to download the code, run it to see what happens, and then read what the code is actually doing. This way you can copy and paste existing code components to use and modify for your own purposes. Arduino program is called the Sketch. It is C++ based language and generally follows traditional structure. There is a preprocessor section where you include libraries or other code and define some hard variables. Setup section where you list stuff you want your controller to do at the start, and the loop, the main section which runs forever repeatedly. Arduino IDE also helps you with color coding, highlighting built-in functions, statements and variables. Let's follow my own advice. Download the first example code, blinking LED, and see what it does. After you turn on the Arduino, it goes to setup section, where there is a command which enables the LED built-in digital pin for output. Each digital pin of Arduino can be set for input, send voltage to the pin, or output, read voltage from the pin. The beauty is that you do not have to memorize the address of the pin or anything. Arduino knows what it needs to do. Each instruction has to be separated by a semicolon. That is a common source of errors and important to follow, contrary to some other languages. There is no more instructions in the setup, so controller moves to the loop, where we have digital write instruction, which sends 1 or high to the pin. This sets the pin to 5 volts and in turn makes LED glow. Then there is a delay for 1000 milliseconds or 1 second, after which we get digital write with low, which sets the pin to 0 volts, hence switching the LED off. Then another 1 second wait, and the loop goes to the beginning, repeating the same sequence over and over again. The final result is blinking once a second LED. There are several necessary and useful programming concepts to familiarize yourself with before you can start coding confidently. The minimum list is on your screen, plus some additional stuff to learn if you would like to become a professional programmer. We will briefly touch each of them. The variables in Arduino have to be declared, meaning the controller needs to know which type the particular variable is. This is done to save limited memory. It can also be used for constraints, but sometimes causes hard to trace bugs and falling planes. So be careful with those and read carefully about each type when using it. The main ones are integer, whole numbers, float, decimal with floating point, and characters. You can also use byte and boolean and some additional types at your disposal. The place where the variable is declared defines so-called variable scope. If you declare it outside of the main loop, it will be global and can be seen from any function and loop. The local variables, ones that are defined inside loops and functions, can only be seen from inside of those loops and functions. It gives you the tool to save memory, as local variables are declared and cleared when function doesn't run, and ability to use the same name for different variables. The scope qualifiers are used to create some specific features. Const declares a variable that cannot change. Static lets you keep the variable inside the memory even when outside of the scope. You might use this to save time for new memory allocation each time the loop of function runs. Volatile type declares the variable which value can be changed by something outside of the main code. We will talk about them later when learning interruptions. When one variable is not enough, there are arrays, which store multiple values of the same type. There are multiple ways to declare them. You can specify the size of the array or leave it open. The access and change individual values happens by specifying the position within the array. See you in the next lecture. Hello! In this lecture, we will learn about loops, functions, and interruptions. If you need to do a repetitive task, it's a good idea to use loops. The most common is for loop. This example loop will start when I equals 0 and execute the command of writing I to analog pin 256 times for each I. Note the scope of variable I, which will only exist within the loop and be destroyed upon the execution. There is also while loop, which executes the statements within curly brackets while the condition in round brackets is true. And finally, do while loop, which comes handy if you would like to check the statement after each iteration rather than before. If you need to use the same action several times under different conditions, you may consider functions. A function can take input variables and can return output variables. The common practice is to declare the function after the main loop, or in a different file. In this example, we define the function with two input variables a and b, which are integers. The function is declared to be integer as well. Inside the function, we compute a plus b. In the statement return specifies the stuff that the function should output. In this case, we output the variable result. Make sure that the stuff that you return matches the type of the function that you have declared. Now, in the main loop, we can use this function and compute a sum of two specific values. There are lots of pre-built functions in Arduino, and the help is great. Plus, there is a very large community where you can download functions that other people have created. The operation of automation is impossible without logical statements, which you can use to create conditional statements. General syntax of if-else is on your screen, and you can use curly brackets to isolate the statements. There are other bits worth knowing and reading about, some of which are specific to Arduino, and you can read about them on their website. For now, we're going to learn about very microcontroller-specific tool, which is called interruption, and revise the cases where you might want to use those. Normal flow of the program is to follow statements one by one in the main loop over and over again. Interruption is the built-in functionality to temporarily stop that and execute something completely different. This is handy for making things happen reliably and can help solve timing problems as well. For example, think about catching the pulses from a rotary encoder so that program never misses a pulse, or trying to read a sound sensor that is trying to catch a click, or infrared slot sensor, photo interrupter, trying to catch a coin drop. In order to use interrupts, you need to declare them beforehand with a specific command attach interrupt, which takes three parameters. The first specifies the pin which needs to be monitored. The second needs to contain the name of the function that executes in the event of interruption. It is called interrupt service routine, and you declare it like a normal function. The third parameter is the mode. This indicates that kind of action on the pin triggers the interaction. Provided example switches the state of LED every time the voltage on the input pin changes. Take a bit of time to read through it and familiarize yourself with it. ISR are a specific kind of function that have some unique limitations most other functions don't have. An ISR cannot have any parameters, and they shouldn't return anything. Typically, global variables are used to pass data between an ISR and the main program. To make sure variables shared between an ISR and the main program are updated correctly, declare them as volatile. Right, if something is still not clear, the following example is really handy to understand what is going on. Our task is to design the pelican crossing controller. What we have is the traffic light, a zebra crossing, and a button the pedestrian can press. It should work the following way. Always green to cars unless button is pressed. If button is pressed, turn red to cars, green to pedestrian. Wait 1 minute and then return to always green to cars. We will simplify this for one built-in LED. On indicates safe to cross and stop for cars, off indicates green for cars and red to pedestrians. And one built-in button. Here's the first attempt for doing this. We will start the loop by checking the button state. Then check if it is high, button is pressed. We will turn LED on and wait for 60 seconds. If the button is low, then we will send off to LED. According to this code, we will keep it off until the button press is detected in the beginning of the loop, where we turn the LED on and stop for a while. Can you spot the reliability and inflexibility issue? The only time the button is checked is short period in the beginning of the loop. Imagine now that we have much more code which takes a while to get through. What happens if button is pressed during the time LED is on? Or what do we do if we would like to let cars go for a while after pedestrian cross to avoid traffic jam? Spend some time analyzing this code until you get the issues. Now let's design an interruption-based code to see how useful it is. Make a note that the button state is now declared volatile, so ISR can actually access it and change it. We have a very simple ISR now called goPedestrian, which changes this variable to pressed. And this happens reliably every time the button is pressed, irrespective of what is happening in the main loop. In the loop now, we are checking the status and immediately change it to unpressed before switching LED on. This way, even if the button is pressed during on, we do not miss this and can repeat the cycle again for the next pedestrian. We can also easily add delay functionality if we want to. I would like you to download this and play around, making sure you understand everything that is going on, and add extra functionality to make it closer to the real pelican crossing. I will see you on the next lecture. Hello, in this lecture we will talk about the stuff that you can actually do with the microcontroller and available functionality around the Arduino controller specifically. First of all, every modern microcontroller would let you to access its internal features, such as memory, digital ports, ADC, analog to digital converter, DAC, or digital to analog converter. Both of those let you interfacing with analog electronics, which is handy and exactly what we want. Also, you have the access to the interrupt control. We have talked about this in previous lecture, and digital timers and clocks. The other important bit is the ability to transmit information to and from other digital devices, such as other controllers and a computer. Most of those is usually organized using serial interface. The general idea for designing embedded system interface is a microcontroller which has several sensors attached to it and controls the outputs such as motors, LEDs, speakers, relays, or transistor-based power circuits. In addition, there is external communication to a computer for performing complex calculations or human interaction. You can obviously connect everything you like to your controller using digital and analog pins. But Arduino has a wide range of standard plug-in sensors and components called shields. So you do not have to use kilometers of jumper cables or design complex PCBs in order to create your own systems. Just plug the shields on top of each other and job's done. Well, enough talking. Let's do some examples. You can find information below on what is Tinkercad and how to start working with it, free circuit and Arduino simulator. I would advise to try to simulate every diagram and code we're discussing here. This will not require much time, but gives you practical hands-on experience even if you do not physically possess Arduino board right now. Let's start with exploring the sensor part. The simple sensor is the potentiometer, or voltage divider. We will connect it between 0 and 5 volts, and will sense the voltage on the middle pin, which should change from 0 to 5 depending on the knob position. We connect this to the analog input pin A0. This simple and touch program changes the frequency of LED blinking depending on the position of the knob by assigning the amount of delay between on or off directly from the voltage value. Arduino has 8-bit ADC, so the range of values received from the ADC is from 0 for 0 volts to 2 to the power 8 minus 1, which is 255 for 5 volts. Moving on, there is the simple button indicator, which sends button state to the serial interface. Next, here's a bit more sophisticated example of using the sensor. This is a standard ultrasonic range detector, similar topology that you might use for car cruise control or parking sensor. Again, the whole program only takes several lines and sends the detected distance of a serial interface every 100 milliseconds. Speaking of stuff that you can control, here is the basic servo control, which turns the servo slowly 180 degrees and then back over and over again. Before we have mentioned serial interface, let's discuss this in detail as we are going to use this over and over again. Serial is used for communication between the Arduino board and a computer or other devices. All Arduino boards have at least one serial port, also known as UART or USART serial. It communicates on digital pins 0 RX and 1 TX, as well as with the computer via USB. Information from Arduino goes through the serial transmit pin TX, as a series of pulses or bits heads serial, following the standard protocol. This information is then stored in the serial buffer on the computer side and can be accessed from a computer. New information is coming on top of the old one, so the computer can access everything received recently down to the buffer size. Information flows the other direction exactly the same way, ending up being stored temporarily in the Arduino buffer, which can be accessed from the Arduino program. In practice, it's good to follow some common sense practices to avoid information misinterpretation and bugs. First, consider establishing handshake, a short preset message exchange to indicate that you have a connection that you are expecting. Then consider confirming the reception of each command, and some basic checks for each message to make sure that your message gets delivered and stuff is actually happening. Finally, buffer size is limited on either side, so avoid transmitting lots of information and cause buffer overflow. Here is a simple suggested structure of communication computer Arduino, which you do not have to follow, but will spare you lots of sleepless nights debugging the misbehavior of your controller. On the Arduino side, there are lots of functions to help you transmit and read serial stuff. Consider reading about those, especially paying attention to data types which can be transmitted and how to read them back correctly. Also consider running the following example on Tinkercad, which reads the serial and lights up the 3-color LED accordingly. Couple of advices on debugging the serial. Use structures you can read and understand to have designed yourself. This way, you know exactly what you're expecting. Particularly, ask yourself the following. Are you sending raw bytes or strings? Did you convert strings to bytes? How about integers? Floating point? Data converters will help you. Also, knowledge of the data types and their byte composition helps. Finally, Arduino IDE has built-in terminal, which lets you see what it is in the buffer and send stuff to the Arduino buffer from a computer. It is located in Tools Serial Monitor. In the end of this lecture, let's have a bit of fun applying some of the stuff we have learned before in Tinkercad. We will build in a non-inverting amplifier based on the LM741 op-amp located among standard components within the Tinkercad environment. Adding 2 resistors, batteries, function generator for the input and monitoring the output with virtual scope, we can physically see how the input signals get amplified. And use our knowledge about control theory and electronics to play around with the gain and bandwidth by changing the resistor values. Here is the diagram and simple code for using Arduino to see the amplified signal and transmit it over the serial interface. I trust you will spend several minutes to understand it and play around with resistors. See you on the next lecture. Hello! In previous lecture we've used some of the stuff we have learned before. This lecture is as practical as it can be, and at the same time we will utilize all of the stuff we have learned before. We are going to use Arduino and Tinkercad to design a PID controller for a DC motor with rotary encoder. You need to remember the PID controller structure and basic algorithm for implementing it. We need to set the demand, the desired position of velocity. Then we need to measure the motor's actual position or velocity and compute the error. We also compute the derivative of the error by subtracting previous error from it and dividing by the time between measurements. Remember the definition of the derivative? Moving on, we update the integral error, which in the very beginning has set to 0. We constantly keep the total by adding current error multiplied by the time between measurements. Again, remembering the rectangular rule for numerical integration. Then we compute the sum of 3 multiplied by their respective gains, and then send it to the motor. The rest is happening automatically, provided that you have selected correct gains. Right, let's see what we're going to need. Arduino Uno, motor with rotary encoder, power supply, T120 transistor for PWM control of motor speed, and a resistor. The first step we're going to do is to establish the measurement of the motor velocity using the rotary encoder. The encoder shines the light through a slotted rotated disc fixed to the shaft and receives it using the photodiode on the other side of the disc. Thus, the diode produces the pulse every time the slot is in between the LED and the diode. Most encoders would have 2 of the LED diode pairs, located in different places to identify the direction of rotation. The time between pulses and pulse duration is proportional to the angular velocity or speed of the motor. The simplest way to read the encoder is to treat it as a switch with a voltage divider connected to a 5 volts through a resistor, and read the voltage from one channel. This is by far not the best way to do it. If you are looking for better ways, Arduino has multitudes of libraries for rotary encoders, but for now it would do for our purposes. So we would drag the motor to the workspace, noting the pinout and channels we want to use, encoder ground, power and channel A. Then we can make it talk to Arduino by connecting ground and power, 10K resistor between power and the channel A, and channel A to the digital pin of Arduino. Then we add some high power to the motor and share ground with Arduino. We will not connect the motor ground pin yet, as we need to understand how to control the speed. Well, remember the transistors lecture? High power current can be easily controlled by voltage connected to the transistor base. We also obviously remember the strategy of controlling the speed through pulse width modulation, and thus connect the base of the transistor through a balanced resistor to PWM output of Arduino. Now the high power current driving the motor will also be pulse-wise modulated and controlled by Arduino. We will also insert some limiting variable resistor serial to the motor power circuit to adjust the maximal speed of the motor. After all, we don't want it to accidentally fly away, do we? Now we want to add a potentiometer to set the desired motor speed, or a demand. After that, we connect a couple of scopes to see what encoder is showing and what the controller output is, and write the Arduino code according to the algorithm we have explored before. As we have already learned about absolutely every single programming tool that is used in this example, I would advise you to write it yourself. The only additional information you would need to know is that it is a DC motor speed control, so think carefully. If you have done it yourself, congrats! Alternatively, you can find the link to Tinkercad below. The whole program is not complicated at all, but now, when you have implemented the PID controller in practice, you can start appreciating the usefulness of theoretical background and flexibility that it gives you in terms of designing new systems. The only remaining thing to do is to tune the gains. As we know, there are several ways of doing it. If you fancy, you can even use the formal control theory, setting up the parameters you want and trying to find a transfer function which satisfies those parameters. Here, however, try to implement the simplest manual tuning algorithm, which is typically applied for such systems. First, set Ki and Kd to 0. Then increase the Kp until the system starts oscillating. Set Kp to half that critical value. Then increase Ki until any offset is corrected in sufficient time. Too much will cause instability. Finally, increase KD until the system is acceptably quick to reach the reference. Too much will cause excessive response and overshoot. Here is the simple illustration of the process observed in the step response. Now, when your controller is tuned and up and running, try to play with the parameters to see what happens if you deviate each gain up or down. Good luck and see you on the next lecture. Hello! This section is all about high-level programming in MATLAB. This is the final step before you will be rewarded by learning how to use acquired knowledge on practice systematically and be able to design your own human-robot interface. We will use MATLAB, however, once you know in one, you can learn another language, like Python, yourself quite easily. We will start by observing the MATLAB environment, which, similar to other high-level environments, offers extended features over the basic IDEs used for embedded programming. MATLAB and similar languages like Python is a very powerful tool for computing and prototyping. It is easy to learn. It is an interpreter language, which means that it executes instructions directly and freely, without previously compiling a program into machine language instructions. So you can type commands and immediately see the result. As usual with all programming languages, we'll start with variables. There are plenty of differences compared to compiled languages. First of all, you do not have to declare the variable. MATLAB will assign a type for you depending on the stuff that you're doing with it. All variables that has been used are not cleared, appear in the workspace, and are constantly located in the stack memory. There are plenty of other features. Some of them are unique to MATLAB, and some, which are common to other interpreter languages, are worth reading about. MATLAB is specifically designed to perform operations with matrices and vectors, which are assigned with square brackets, where rows are separated by semicolons with those brackets. Numerical sequences can be assigned with colons, where the step size can also be defined and defaults to 1. All major matrix operations are overloaded, which means you can use the multiplication symbol to perform a matrix multiplication, or division symbol to perform matrix inversion. You can also perform element-wise operations by adding the dot in front of the sign. For example, A dot multiply B will multiply each element of A to a correspondingly located element in B. Element of a matrix can be accessed by location using round brackets, where row comes first and column second. You can also create multidimensional matrices if you want to. One entire row or column of a matrix can be accessed by a colon sign instead of a position. And the matrices can be collapsed into vectors using single colon in brackets as well. One important thing to notice is, contrary to most languages, numeration in MATLAB starts with 1 instead of 0. So if you need to access the first element of a vector, you write V1 instead of V0 in Arduino or C. Annoying, I know. MATLAB has huge, and I mean huge, number of built-in functions literally from all areas of mathematics and engineering, ranging from a simple like mean to a very specific complex functions like BSX fun. The real trick to MATLAB is learning which functions exist and how to use them. If you want to perform some operation, just Google it. A function will exist. The standard syntax for all functions is this. You need to specify output variables, which will be stored in the workspace, and pass input variables, which either already exist or created inside the function call. Here is the list of simple functions for you to start experimenting. You can store and load the variables and data using specific .mat format. You can utilize the environment build buttons, or use it in the code employing save and load functions. You can also save and load comma-separated text files using the commands dlm-read and dlm-write. Similar, you can employ imread and imwrite commands to read images into matrices and write matrices into image files. Apart from matrices, there are strings, cells and structures. Each one is good for a specific reason, so worth reading in the additional material. There are a number of functions for conversion between those types, in addition to usual numerical type conversion functions. To start programming MATLAB, you either type the command in the command window or start a new script, the file that has list of all commands which will be executed sequentially and has the extension .m. It is good practice to annotate the code using the commands, which start with a % symbol. The code can also be divided into the cells, with a double % symbol separating the cells. All code in the cell can be executed by pressing Ctrl-Enter when your cursor is on the cell, directly from the script file. This way, you can easily debug chunks of code without running everything, by testing the result in each cell. Obviously, like in any program language, you can use loops, for and while. The syntax of those is on your screen. Operation is similar to the previous loops we have learned, with a slightly different syntax and the fact that you do not have to declare the variables. Also, general rule is to avoid those in the code, as in comparison to compiled languages they are very slow. Consider using matrix operations or built-in functions instead. Conditional statements are also there, if-else, with a specific set of logical operators. Some of them operating structure-wise to the entire matrix, and some can operate element-wise. There is also a switch case structure, in case you are checking for the set of possible values for the same variable. You can obviously create your own functions. Simplest way is to convert the existing script into a function by the following syntax, specifying input and output variables. Any commands that you write on the top of the function will also be read by MATLAB help art routine and correctly displayed. Unlike scripts, which can see all variables in the workspace, functions use their own private workspace. So be careful when assuming you have already got some structure in place. A function will not see it unless you pass it to the input. Similar, none of the variables declared in the function will be seen outside of it, unless declared on the output. MATLAB has very powerful built-in debugging for scripts and functions. Potential errors are underlined in red. They are also highlighted by orange or red marks in the warning bar. MATLAB will suggest solutions to these potential errors, but they are not always appropriate or correct. Despite this, MATLAB cannot detect all potential errors, so be careful. You can make use of those specific debugging mode. This is initiated by clicking in the left-hand bar, by the line numbers. Your code will then only run to that line, where a red dot will appear. This is called a breakpoint. Clicking on the breakpoint again will remove it. A small green arrow will indicate current position within the code being executed. You can subsequently step through your code one line at a time, which allows you to identify the location and source of errors. You can escape the debug mode by executing dbquit command or clicking on the appropriate button. See you in the next lecture. Hello! In this section we will finish learning about basics of MATLAB. The essential bit of any high-level programming, especially for science and prototyping, is the ability to represent the data graphically. MATLAB offers a very simple and powerful tools for doing this. You can create a basic line graph in MATLAB using the function plot. Plot y will plot your data y against an arbitrary numbered x-axis, whereas plot xy will plot your data y against the corresponding x-axis allocations in x. If y is a matrix, the plot function will display all columns of y as separate lines. And if your data is arranged in rows, use the apostrophe shortcut to transpose the matrix. You can create a basic line graph with error bars using the function errorbar. Also, scatter plots can be created in MATLAB using the scatter function. The plot function automatically generates a new figure window, if one isn't open yet. However, it automatically overrides an existing figure row. So open an additional figure window, use the figure command. To add lines to the existing figure, you can use the hold on, hold off commands. You can close figures individually with close, or close them all with executing close all. MATLAB automatically scales figure axis to accommodate the data being plotted. But you can control this manually using xlim and ylim commands. There are several functions for adding labels, titles, and text to figures. Text added by these functions can also be formatted directly from the command line. This is achieved by passing additional inputs to the function. There are two ways to edit the properties of a figure. The first is through the figure window toolbar by clicking Edit Figure Properties. The second is directly from the command line. Basic properties can be defined when first creating the plot, with the specific shortcuts for color, marker size, and line style. More complex properties can be adjusted using set function. The figure handle here identifies the figure that we wish to edit, and you can use the shortcut GCA, which specifies the current figure. Several different panels can be plotted within a single figure using subplot. Panels are numbered among each row. For example, subplot 221 sets up a 2x2 square of panels and plots in the first. Plots can also be spread across multiple panels. When drawing subplots, figure handles can be used to control each panel separately. Assigning variable to each panel. This is achieved by providing the subplot function with an output variable like so. Properties of that specific panel can then be controlled using command set. Vertical and horizontal bar charts can be created using the bar and bar h functions, and histograms can be created using the hist function. Two-dimensional plots can be created using contour F and image SC. Note that the input for those is a matrix, where each value corresponds to a color to plot. There are many other different plotting functions within the MATLAB. Each of these can be controlled using the general syntax discussed above. Moving on, it is useful to discuss programming practices. The basics are: assign variables early, make your code easily expandable and adaptable. Go from simple to complex. If you're faced with a complex issue, develop a toy model first. Use modular programming. Create functions when possible. Back up your code before you have changed it. Make extensive use of commands. And finally, don't have faith. Always test your code with simple examples. It is also important to optimize your code in terms of memory and processor requirements. Some basic rules can help you to avoid sluggish script and may play a decisive role in making your script runnable at all. Pre-assign arrays and don't let them grow inside of the loops. Avoid loops when possible, they are slow. Favor matrix algebra. Favor logical operations over the built-in functions like find and non-zeros. And consider using sparse matrices, although note that sparse indexing is also quite slow. In the end, let's talk about some specific MATLAB features which are essential for embedded system-to-computer interface. We are going to be using them in the final section. The convenient way for communicating to your microcontroller, as we discussed previously, is the serial interface. Here is the set of commands that will enable this functionality from the computer side. Essentially, you need to open the serial port, set up the baud rate, and open the serial. Make sure that baud rate matches the one from the controller side. Then you can transmit the stuff or read a value from a buffer into a particular variable. Don't forget to close the serial and clear it after you've done with it. Otherwise, it will stay open and you wouldn't be able to open it again in MATLAB. The useful commands to execute closing everything is close all and close insert find, if you want to shut down everything forcefully. Finally, it is worth noting the digital filtering toolbox, which offers a powerful set of tools to get your signal filtered. This doesn't replace anti-aliasing filter, however. For everything else, you can use it to essentially emulate the analog filters and sometimes even overperform them. The stuff comes at a cost of processing power, but since in most cases it's not a concern for modern-day computers, all of these tools can operate real-time these days. The syntax is also quite simple. You first need to create a specific filter. Depending on the application, there can be many varieties. You can use simple Butterworth filter of nth order, given it the order and the cutoff frequencies, or use the sophisticated design field command. These even have a user interface and lets you choose among different filter types and configurations, while at the same time control cutoff frequencies and ripples. You need to output the filter to a variable and then use this variable with a field command. You give the field the variable and the data which it needs to be filtered, and it outputs already filtered data. If you use the matrix data, then columns of the matrix will be filtered independently. It essentially treats the first variable as time and second as independent channel number. Alright, now we have learned everything we need. I will see you on the final lecture where we will finally design and implement the active bionic prosthetics. Hello and welcome to the final lecture where we're going to design a human-robot interface in form of robotic prosthetics. We should start with the problem outline. So we have a robot and we wish to control it seamlessly using smooth human interaction. Of course we can use joystick or keyboard interface, but our task is to design something which would work intuitively and in addition to other tasks the human can perform in the meantime. Bionic prosthetic is a good example of such device and acts as a demonstration for the platform of tech possibilities that you can employ to instrument such systems. Remembering the general structure of embedded system, we will split it to a sensing part, control part and a computer component. The control part is easy. All robotic systems are an assemblies of motors and actuators of different sort. We will simplify the system to control a single finger, which in turn can be represented as a motor, which is normally employed to move that finger. In fact, we could generalize it with the generic transfer function, but motor is more illustrative in this case. The sensing part can be also generalized as a signal in time. However, we're going to be using the EMG. Remember from the first section that this is a voltage difference signal, which we can sense from the surface of, say, hand using the electrodes. The physiological origin of the signal in so-called muscle action potentials, which occur when muscle fiber contracts, and in fact is the direct cause of this contraction. With more frequent activity, the muscle contracts stronger. Also, with more fibers involved, we start to get more of these action potentials from different places. In the end, from a sensor perspective, the amount of chaotic activity in EMG is generally proportional to the force of muscle contraction. The overall characteristics of the signals are following. It is stochastic, has a frequency band of 1 to 100 Hz, and it needs amplification, as the order of magnitude is millivolts. These potentials are stronger if they are closer to the electrode, so the single electrode contains most information about nearby muscle. We can use several electrodes located above different muscles to resolve complex motion or gestures where several muscles are active. So again, without loss of generality, we simplify the system down to one motor and one EMG sensor, knowing that we can add more sensors and motors to the system if we need to. Let's draw a diagram of this, noting the signals flow. From human, EMG needs to be amplified, filtered, which we already know how to, and sent to the controller. Controller needs to control the motor real time, and by mere coincidence, we already know how to do exactly this from the last lecture of the third section. The central brain of the system is a computer, which communicates with the microcontroller by reading the EMG signal and makes the decision by generating demand or desired motor speed. Once we have established the system operation, this architecture ensures reliability and real-time performance for the key components which we do not need to modify, and great flexibility in experimenting and tuning by just using the high-level software. Here is the list of components we would need. First, we need all the stuff for the motor control from section 3. In addition, we will use Olimex Arduino EMG shield and sticky EMG ECG standard electrodes. The Olimex is a shield with built-in amplifier and filter, and the sticky electrodes are basically pads with conductive gel that you can connect to a wire. They are standard and available even online. This is how the full assembly should look like. You would use 3 of these electrodes, 1 ground and 2 for connecting to the amplifier, which, if you remember, amplifies the voltage difference between them. You would position one over the muscle and the other over the skin away of any muscle to act as a stable reference. Now we can start with the controller setup. We need to read the signal from the shield, so we would want to understand which pin to read and follow the instructions from the shield manufacturer for specific clock settings. Then we need to organize the data structure, or we can ignore all of this and open the example included in the Olimex package. Let's go over the preprocessor and setup. The file sets up some basic data structure already and uses 70 bytes in data packets, which is basically an array. First 4 bytes are used for the header. We can safely ignore them for now. Then there are 12 bytes for 6 channels. Each channel will use 2 byte, 16-bit resolution per channel. And yes, you can connect up to 6 of Olimex shields stacked on top of each other in order to have 6 channels. This is a good example of code which accounts for future expansions. The code uses timer interruptions to establish the reliable sampling rate of 256 per second. Here is the declaration of timer to overflow interruption, which occurs every 1/256th of a second and runs the timer to overflow ISR. The last bit of setup code establishes serial communication. There is basically nothing in the main loop. All the stuff is happening in the ISR. Let's go over it. Ignoring the malarkey of switching LED, there is a loop which goes through the channels 1 to 6 and reads the associated analog pin. Then the value gets converted from integer to 2 bytes and stored in the array in the appropriate positions for each channel. After the loop is done, we're sending the array to the serial one by one, ignoring another maintenance malarkey, which is not important. That is basically it. We have organized the seamless 256 a second digital data transmission. As an exercise question to check yourself, what do you think is Olimex anti-aliasing filter cutoff frequency? Right, next bit to organize is the computer side of things, to read the data and make the decision on motor speed, sending it back to controller. We will obviously use MATLAB, so let's briefly go over the setup and actual operation. First, we open the serial, remembering to check baud rate to be the same as in Arduino. Next, we are setting some parameters we are going to need for plotting. We want to plot 1 second, but we also want to make it flexible. And the data structure we are going to use. Here we have selected just 2 channels for now. Each will have 256 values, or 1 second stored. And we will use this as a circular buffer. When the array is filled, we are going to start recording it over again, like a clock. Now we will set a graph, where we plot the data. The strategy here is to preset everything like window and plot parameters and just update the data itself to save time. Okay, we go into actual operation loop, where we set the sample number to 1 and start the loop while the window is there. This way, upon closing the window, the loop terminates automatically. We check if there is something in the serial buffer, and if there is enough information for us to read, we read the specified number of samples, which in this case is 20. It gave a good balance for my laptop between the speed of reading the data and speed of doing everything else. Now for each sample, we read the structure from the buffer and assign the first channel of EMG to our first channel of data, converting it from bytes to double precision numbers. Then we increment the counter, remembering that if it reaches the end of the array, 256, or 1 second, it should start from 1 again, overwriting the first values as circular buffer would. Then we update the graph, after which we make sure that the buffer does not overflow by growing too fast. In the very end, we note a statement that closes the serial in case we have closed the window. Phew! That is it. Now when we start the Arduino and start our MATLAB script, we will see the EMG in real time on the screen. The only thing left to do is to make a decision on the demand, our motor speed, based on what we receive. The usual way to compute the spread or power of the stochastic process, proportional to the muscle activation in our case, is to compute the standard deviation, which is equal to root mean square in case of zero mean signal. In our case, that gives powerful way to control the motor action, for example by just making the speed to be proportional to RMS. This makes some sense. No muscle activity will produce no motion, and more active action would produce faster motion. It's not ideal, but that's a beauty of high-level programming. We can easily add more complicated stuff later. We can leverage the power of MATLAB, adding simple code to compute and display the RMS on a second graph. Then we can scale it, balance the maximum speed, if you want, to the maximum RMS your muscle can produce empirically. And finally, send this back to Arduino in order to set up the speed. I trust that you can do it yourself like a no-brainer now. In summary, we have created a closed-loop speed-controlled motor finger operated real-time by EMG muscle activity. Now we have the structure in place, it is clear to see how we can easily expand on this. Several fingers controlled by several sensors, or more sophisticated analysis to control the motors better? In the very end, there are questions to ask yourself. Can you comfortably replace motor with a linear actuator? Can you control forward-backward motion? Can you make the system to sense additional parameters, pressure when touched, temperature, etc., given appropriate sensors? Can you think of a way to analyze this data in MATLAB and send back improved demand for the motor? Can you make the MATLAB code which expands on this and incorporates more ideas? If the answer to all of this is yes, then I have successfully achieved my goal. I wish you all the best, and bye-bye.